In the Electron 4 session, we indicated that no two electrons will have the same 4 quantum numbers. That's called the Pauli exclusion principle. And we're just going to put some numbers to the test to check this out. And we're going to deal with the element sodium. If you look on the periodic chart here, what's the atomic number of sodium? It is 11. That means it has 11 protons in every nucleus, but it also has 11 electrons. And I have the electrons listed at the left here. Now we're going to build the sodium atom. We're going to start the off-bow principle. It has 11 electrons. The first one goes to level 1. The second electron completes that orbital. That's the second electron. The third electron goes to the second energy level 2s. Next electron completes that orbital, that's sublevel. Now you go to the p subshell. And as you start adding electrons here, we've added 4. Now we go 5, 6, 7. That is called the Hun rule. The Hun rule, very important. The Hun rule says that in any degenerate orbitals, where the orbitals are the same energy, each orbital is filled halfway. That is greater stability. In fact, half-filled sublevels are more stable than individually filled, one-filled. Now that's 2, 4, 5, 6, 7, 8, 9, 10. Now that's a noble gas configuration, and the 11th electron is here. Okay, now we're going to use the symbols. N, remember, the numbers goes from 1 to 7. So the first electron is in the N equals 1. Then if you look at all these electrons, 2 through 10, they're all in the 2 level. I just put these all down, 2. Second quantum number, and this electron number 11, is in the third quantum number, or third number, in the principal quantum number. Say it right, getting sloppy. Now, let's go to the shapes. These are S. The shapes, if you remember, are SPDF, and the symbol for that second quantum number I haven't used is the letter L. You look over here, it's L. And those numbers, quantum numbers, are 0, 1, 2, 3. That's SPDF. Okay, so the first quantum number is for the first electron, and the second electron is 0. And then you go to 3 and 4. That's also 0. Now 5, 6, 7, 8, 9, 10. Now you're at 1. That's the P. Now you're back to S shape, which is 0. Okay, now this is basically giving a quantum address for each electron, left and right. Now let's go to the direction. The direction of, and this is called the directional quantum number, or azimuthal. And for S, the direction is defined as 0. There is no direction for a sphere. And P, it goes from a 1, 0, minus 1. All right, and that's all we need. D is 2, 1, 0, minus 1, minus 2. So let's start here with the direction. The direction for number 1, of course, is 0, 0, 0, 0. They have no direction. They're a sphere. Okay, we used the first 4 electrons. Now look what we do. And we're going to follow the Hun rule. And it's just a protocol. We go from 1, 0, -1, left, middle, right. So the quantum number here for 5, the fifth electron, the p electron is 1. And this is 0, and this is -1. Now you start again. 1, 0, -1. And now you're back to the direction of the sphere, which is 0. Now, the spin quantum number, S, is a plus. It starts with a plus 1/2, then a minus 1/2. All right? And we're going to just skip the plus and just use the minus 1/2 sign, because plus, without listing the plus, it means plus. So we're going to follow a protocol of starting with spin in one direction, spin up, and we'll call it clockwise spin. So the spin first electron is 1/2. The second one is spinning the opposite direction for a magnetic coupling, minus 1/2. Now we go to 2s, it's 1/2, then minus 1/2. Now, the next 3 orbitals have to be parallel spin, because you're filling each orbital. These are called degenerate orbitals, same energy level, degenerate. You're filling each one halfway. So it's a plus 1/2, 1/2, 1/2, 1/2. Now the next 3 are spinning counterclockwise. Minus 1/2, minus 1/2, minus 1/2. And now you're back to plus 1/2. Okay, now so what did we just do here? Well, we have to now look left and right and see if Pauli's exclusion principle works. And I see a mistake here. This should be 1. You should have told me that. Okay. First principle level. Okay, so the first 4 numbers, they are different because of this 1/2. Now you go up to the next one, the 2s are all different. See, it's plus 1/2 and minus 1/2. The 3s, I got a little messy. Look them over. They're all different. So all these electrons in the sodium atom are unique. The set of 4 quantum numbers. If this is a sodium atom, now notice it has 11 electrons. Watch what happens. If I remove 1 electron, I've gone from a sodium atom to a sodium ion. It's 1 plus. And notice what the sodium ion looks like. It looks like neon. So this is the reason why the sodium ion is so stable. It has a noble gas configuration. It's called an octet. 2, 4, 6, 8 electrons. 8 electrons. We can look at the periodic chart here that we're putting up next. And notice sodium and the group 2 elements are both focusing on their outer electrons, or s electrons. Now you go over to periods 13 through 18, or we could sometimes call them 3a through 7a and 0. Those are the p shapes. And then the transition metals are D, and the other transitional metals are what we call the transuranium metals are F. We will be stopping right there.